Evaluating limits. For the most part, when you're trying to evaluate limits, you want to just go ahead and try to plug in exactly what you're approaching. So as x approaches c, just try plugging in that number in. A lot of times it'll work, but not always. And so your first step in evaluating limits is just to go ahead and plug in that value. And that's exactly what this theorem down here on the bottom is saying. Saying if you're trying to take the limit of x, just plug in c and that's your answer. If you're trying to plug in or deal with x to a power, just plug in c and that's your answer. Now these theorems are saying, well, if you start off with two functions where the limits exist, so the limit is x approaches c of f is L, limit as x approaches c of g is k. Well, if you just multiply your first function by a number, well, your limit's just going to be your limit times whatever number it was. Here, if you have things added together or subtracted together and you're taking your limit, just take the limits of each one and then add or subtract. Same thing with multiplication and division, with the exception of when the bottom is 0 and you can never divide by 0. In essence, when you're trying to take a limit, just go ahead and plug that value in. If it works, great, that's your answer, you're done. If it doesn't work, then it requires a little bit more work. So, whenever possible, just try plugging in the number. So here's 3. Plug it in, 3 squared plus 2 times 3 plus 4, and we get our answer. Same idea on the one on the right. Just try plugging it in. 2 times 3 plus 5, 3 squared plus 2 plus 4. Plug it in, you get your answers. Well, you want to do that for all of them as your first step. So when we're looking at our limit as x approaches 1 here, when you plug in 1, of course you get 1 on the top because that's not going to change. Then you get 1 squared, which is 1 minus 1. So you get 1 over 0. Oh, we can't divide by 0, so we got to use a different approach. But you will realize that the bottom is differences of squares. So it's like, okay, what can we do here? Well, let's go ahead and try a number just to the right of 1. And so that's what I mean by this little plus sign as kind of like an exponent. That means what happens if I try numbers slightly greater than 1? Well, if I try a number slightly greater than 1 and add 1, well, that's basically going to be 2. If I try something slightly greater than 1 and subtract 1, well, then that's a really small but yet positive number. Well, let's see. If I double a small positive number, it's still small positive. 1 over a small positive, well, 1 over a positive is positive, but 1 over a small is really, really big. So in other words, it's positive infinity is what it's diverging to when you try a number slightly to the right of 1. Well, you want to use that approach also coming in from the other side. What happens is I look at a number slightly to the left of 1, and that's what I mean by that little negative exponent. That means you want to try numbers slightly smaller than 1. Well, of course, the top's still going to be 1. You try a number slightly smaller than 1, and you plug it into your x plus 1, and well, it's basically 1 plus 1, so that's where we get the 2. Numbers slightly smaller than 1, like the 0.9999 stuff, minus 1 is just a negative, but just barely negative, so it's a small but negative number. Small meaning close to 0. So now you got to double a small negative. It's still going to be small negative. So a positive 1 divided by a small negative is going to be a negative in answer. And 1 over a small is big, so it's a big negative number, so negative infinity. So, are we approaching the same thing on each side? No, we're not. So therefore, there is no limit since the left-handed limit and the right-handed limit are different. So we're going to continue on here. We're going to try to go ahead and just use that direct substitution. Just plug in what we have. So we're going to plug in 2. You plug in 2 on the top, you get 4 minus 4 is 0. You plug in 2 on the bottom, you get 4 plus 2 minus 6, which is 0. You get 0 minus 0. That's an indeterminate form. We can't evaluate it when it's like that, so that means you got more work to do. So you'll notice the top is differences of squares. The bottom is a nice trinomial that factors. Well, you'll notice, oh, same factor top and bottom. So with the same factor top and bottom, you realize that they cross out. So you're really left only with your limit as x approaches 2 of an x plus 2 over an x plus 3. Now we're going to try that direct substitution. You want to go ahead and you want to plug in 2 for your x. Well, 2 on the top, 2 plus 2 is 4. 2 on the bottom, 2 plus 3 is 5. So you get 4/5. So whenever possible, do that direct substitution. If it doesn't work, that means you got a little bit more work to do. If it does work, that's great. You're done with the problem then when you plug it in. So looking at the next problem, we want to see, does it work to just plug in 4? 4 squared is 16. 16 plus 9, oh, that's just 25. Square root of 25, well, that's 5. So, hey, it works. Great, we're done. We move on to the next problem. Plug in our 4. Do a little bit of simplification here. Get 24 plus 40. Cube root of 64. And you should know that that's just 4, so that's your answer. Limits of trigonometric functions. Well, basically, you can go ahead and figure out your limits of any trig function just by plugging in the value, assuming you're not at a point where there's a vertical asymptote. So we could try plugging in -3 here, but once again, you get 0 over 0, which is an indeterminate form, so it's like, oh yeah, that requires more work again. The bottom doesn't factor, but you'll notice the top does factor. Factors into 2 parentheses nicely. You'll notice, oh, same factor top and bottom, so you're going to cross those out. You're left then with just the limit as x approaches -3 of just that, what's left in the parentheses, x minus 2. Plug it in then. Get -2 minus 3, which is -5. That's it. You're done. Looking at the next one up here, your limit as x approaches pi of cosine. Just plug it in. You should know that one from your pre-calc or trig class. And you just get -1. So when you're dealing with trig functions looking for your limits, once again, just plug it in just like you would with a normal problem like you have there on the left. This one here, we're dealing with a root. We tried to plug in 0 for your limit using that direct substitution. Well, that gives us that 0 over 0 stuff, which is an indeterminate form, which means we have more work to do. Well, typically rationalizing the numerator is going to help you out. So that means you got to multiply the conjugate. So we take our original problem, multiply the top and bottom by the conjugate at the top. That's the same as what you have on top, but you just switch the sign from a minus to a plus. Make sure you multiply the top and the bottom both by the same thing. Then you're going to FOIL the top. Remember, in multiplying conjugates, you multiply the first terms. Your outer terms and your inner terms drop out. Then you do your last terms. the bottom, I'm not going to really multiply out. I'm going to basically just rewrite the bottom. You'll notice that the top does simplify. Top just simplifies down to x. So now you have an x times the whole top and an x times the whole bottom. Then you can cross out those x's in front. So you're left with only a 1 on the top, and you're left with your conjugate on the bottom. Now you can actually go ahead and plug in 0. Plug in 0, work it out, you get 1/2. Now we have the squeeze law. If f is always smaller than g and g is always smaller than h in a particular neighborhood, and you happen to know the limit as x approaches a of f is L, and you know the limit as x approaches a of h, well, therefore, you can imply that the limit as x approaches a of g is also L. Because if you know your two outer limits, and they're both the same thing, the center limit would have to be that. You can actually use the squeeze law to actually prove this right here has a limit of 0. There's details on how to do that on my website if you want. Now, if you look at the graph, we're going to start off with 3 functions of a negative x, which is always less than or equal to your x sine 1 over x is always less than or equal to your x. If you graph your sine or your x, that's what we have in blue on our graphs. If you graph your negative x, that's what we have in red on our graphs. You'll notice that the green is what we're looking at. You'll notice as you come in from each side, all the functions kind of go down towards that 0, 0, the origin. You'll notice the green is always going between the red and the blue. Well, if we just zoom in on this area right here, we get the graph over here to the right. And you'll notice, once again, it continues to oscillate in between the green and the blue. Well, it's obvious to see that the limit of the blue is 0, the limit of the red is 0, and you can see looking at this graph then that the limit of your x approaches 0 of x sine 1 over x also is 0. That's your squeeze law. Oh, one other comment here. We can't actually go ahead and use the product rule here because it would be plugging in your 0. It would be 0 times the sine of 1 over 0, which is undefined. So it would be 0 times undefined, which is meaningless. Here's your basic trig limit on the left. Have it memorized. Here's another limit on the right that you need to have memorized. We're going to be using these to be able to work out our problems. So we're going to start off with this, the sine of 3x over x. To try to use your basic trig limit right up here, what's after your sine right there has to be the same as what's underneath in the bottom of the fraction. So we don't have that here. We have a 3 after our x. So to be able to try to use any basic trig limits, we've got to have a 3 after the x in the bottom. So I can put a 3 there. But if I multiply the bottom by 3, I then got to also multiply the top by 3. So I have 3 times my limit. Now, to technically use my basic trig limit, I can only have one thing here, not necessarily a 3 in front of it. So I'm going to let y represent 3x. So on the top, instead of having the tangent of 3x, I'll have the tangent of y. And remember, tangent is sine over cosine. So I'd have the sine of y over the cosine of y, replacing my 3x in the bottom with y. And then my top would just be 1 here, because remember my cosine's on the bottom. Here, the first part's just my basic trig limit. So it'd be 3 times my basic trig limit, which ends up being just 3 times 1. Now, when I'm looking at evaluating the last part, all I have to do is just plug in 0, because the cosine of 0 is 1. So it'd be 1 over 1, so I get 1. So it'd be 3 times 1 times 1, so I get a limit of 3. Go ahead and try the next one and pause the video. So we're going to use a very similar approach here. We're going to break it up in terms of sines and cosines because we want to use our basic trig limit. You know that tangent is sine over cosine. We still have our x on the bottom. We'd have a 1 on the top over there. Apply the limit to each fraction. Evaluate each fraction. Your first one's your basic trig limit. Your second one, you can actually just go ahead and plug in 0 and you get 1. So you get 1 times 1, which is 1.